All right, here goes part two. So these are the trends for electronegativity. If you have a paper copy of the periodic table and you want to add it to that, you're very welcome to. So that increases from left to right and it decreases from top to bottom. All right, so student response sheet. Why do fluorine, chlorine, bromine, and iodine all have a high electronegativity? Why does electronegativity increase across a single row? And why does it decrease down a column? Answer to the best of your ability, and I will talk you through it in a moment. So fluorine, chlorine, bromine, and iodine are all in a family right here, and they all have very high electronegativities. The reason for that is these column 8 has a full octet, and these guys are so close, right? They only need one more electron to have that full stable octet, so they really, really want an electron. It would be very energetically favorable for them, and so that's why their electronegativity is so high. As you go across a row, for example, lithium to beryllium to boron, carbon, nitrogen, oxygen, fluorine, the electronegativity increases because you're adding a proton every single time, and that increases the power of your magnet. So right here, it's like magnet 3, magnet of 4, magnet of 5, and so on. And so it gets a little bit stronger at attracting electrons as you go across. When you go down the row, even though you're getting, or down the column rather, even though you're getting more and more protons, you are putting another layer of electrons in the way. So this is one ring, so there's nothing between the proton and the valence electron. This has one ring between the nucleus and the valence electrons. This has 2 rings in the way, 3 rings in the way, 4 rings in the way, 5 rings in the way, and finally this last row has 6 rings in the way. So if you have 6 rings in between the nucleus and the valence electrons, it's just really hard for the nucleus to hang on to those valence electrons. And so the electronegativity decreases because it can't attract them, because its magnet is not even really strong enough to hang on to the electrons it already has. So shielding definitely has a huge effect on electronegativity. Okay, so now using this table, figure out which one has a smaller electronegativity and then tell me why. Is it because it has fewer protons, so it has a weaker magnet? Or is it because it has more shielding, so it has more layers in the way? Take a moment and go ahead and do your best. All right, so now we want to look at the solutions. So for aluminum and chlorine, aluminum has a smaller electronegativity. These guys are in the same row, and so their shielding is equal, which means that the only thing affecting them is that aluminum has fewer protons. So aluminum has the weaker magnet, therefore it is not as good at attracting electrons. Magnesium or aluminum, magnesium is also in the same row as aluminum, but magnesium has less protons than aluminum. So magnesium has the smallest electronegativity. If we compare calcium and cesium, cesium is lower on the periodic table, and so it has more shielding than calcium, which means that cesium has a smaller electronegativity, even though it has more protons. If you have more shielding, doesn't matter how many protons you have, shielding just messes everything up in terms of trying to attract electrons. Nitrogen or bromine. Bromine is in a lower row, and so it has more shielding, and so it's not as good at attracting electrons. And then lastly, we have gallium or potassium. And so potassium is in the same row as gallium, but it has less protons. So gallium is stronger than potassium. Potassium has a smaller electronegativity. Now we want to start applying this idea of electronegativity and the difference in electronegativity to some molecules and compounds, so we can understand how it affects chemical bonds and the way chemicals behave. Here we have three different compounds. So the first one we have is chlorine, Cl2. The second one is hydrochloric acid, HCl. And the last one is sodium chloride, NaCl. On your student response sheet, please answer, what are two similarities between images 1 and 2? What are two differences between them? What kind of bond does each of these things have? Take a minute. Alrighty, so two similarities between images 1 and 2. They both have chlorine, so that's something that you could say. You could also say that the atoms are depicted as touching in 1 and 2, and they're not depicted as touching in 3, so maybe that's significant. Some differences, the second one has hydrogen, whereas the first one only has chlorines, and the hydrogen is really, really tiny compared to the chlorine, right? So those are some observations we could make. What kind of bond is each of these? So chlorine is a nonmetal, and so this is a nonmetal stuck to another nonmetal, so that is a covalent bond. And then, Micah, get out of here. Let Tino have his treat in peace, you bully. So then, for number 2, hydrogen acts like a nonmetal, chlorine acts like a nonmetal, and so we have another covalent bond. For number 3, we have a metal. Sodium is a metal, and chlorine is still a nonmetal. It will always be a nonmetal. And so that is an ionic bond. And this little plus next to this Na and minus next to Cl just kind of confirms that it is indeed an ionic bond. Okay, so let's take a look at these now in terms of their electronegativities. In your student response sheet, figure out the difference between the electronegativities in image 1. So you're going to take the electronegativity of chlorine and subtract the electronegativity of chlorine. That would be hard math. Then electronegativity between the things in 2. You're going to find electronegativity of chlorine and subtract the electronegativity of hydrogen. And for 3, you're going to do the same thing by finding the electronegativity of sodium, and you'll subtract the electronegativity of sodium from the electronegativity of chlorine. So go ahead and do that real quick or real slow, whatever you want. Pause the video, take your time. Okay, so if we talk about this for a second, the 2 chlorines, their difference in electronegativity is going to be 0. Nobody is winning that tug of war. For HCl, the difference is 0.9. Okay, so 3.0 minus 2.1, 0.9. So that tells me chlorine is winning tug of war, right? It has the bigger electronegativity of 3.0, and so chlorine is sharing the electrons unevenly. It's pulling the electrons closer to itself, and hydrogen is too weak to do anything about it. It's just kind of like, I guess I'm grateful we're still kind of sharing. Then we have example 3. And so sodium's electronegativity is only 0.9, and chlorine's electronegativity is 3.0. And so 3.0 minus 0.9, that's a huge difference in electronegativity land, because that's a difference of 2.1, and that means it's ionic, right? That chlorine is so much stronger than sodium that it can just rip sodium's valence electron off, and sodium's like, oh, okay. And actually, it works out okay for sodium too, because then sodium has that full outer 8 exposed, And so it gets to act like it has a full octet, and then chlorine gets one extra. It normally has 7 valence electrons, so now it gets to have a full octet, and there was much rejoicing. All right, so basically this means there are 2 types of covalent bonds. Nonpolar covalent, where the electrons are equally shared, and polar covalent, where the electrons are unequally shared. So I would go ahead and write this down. Draw yourself a little picture of our 2 examples so that you have an example, excuse me, of a polar and a nonpolar covalent bond. Polarity is actually much simpler than it sounds. It's just a separation of charges. And so pole actually means end. That's why we have the poles of the Earth, the North Pole and the South Pole. When molecules are polar, they have what we call a dipole, di meaning 2, pole meaning pole. So we have 2 poles, or 2 ends. One side of a molecule is slightly positive, and one side is slightly negative. So this time, please draw this little hydrofluoric acid dude into your notes, and draw, right, we have this weird delta plus, we have delta minus, we have the plus arrow. Kino, can you get off of me, please? You guys, the dogs are going crazy. Yeah, so fluorine's a little bit negative, hydrogen's a little bit positive. Make sure you draw the deltas and the plus and minus and the arrow all into your notes. So polarity and electronegativity are related because polar molecules have unequal electronegativities and the dipole gets formed. So one atom is pulling very aggressively on the electrons. Nonpolar molecules have equal electronegativities, and so they have no dipole. They're just chilling, right? They don't have a positive side or a negative side. They're neutral. On your student response sheet, go ahead and try to predict some polarity, and to indicate what you think, just draw the arrow over the top. So you can predict it by looking at the difference. So for aluminum and oxygen, the 3.5 minus 1.6, so 1.9 is the difference. I think that might be math. And that is a large difference. So it's definitely going to be polar, and the oxygen is stronger. And so the arrow will point towards the oxygen, and the plus end of the arrow will be over the aluminum. Do this in your student response sheet, and then I'm going to walk you through the rest. Okay. Carbon and hydrogen are almost equal, 0.4, so they are nonpolar. And then Mg and Fe, so magnesium and iron, difference of 0.5, that's a metallic bond, and so that's not going to be polar. Nitrogen and oxygen are next door neighbors. They're only 0.5 apart, so they are going to be nonpolar. Carbon and fluorine are a big difference, so that will be polar because it has a difference of 1.5. Phosphorus and oxygen has a difference of like 1.3, big difference. Oxygen's bigger, so oxygen will have the head of the arrow, so that is polar. Beryllium 1.6, oxygen 3.5, definitely going to be on the polar side. Oxygen will be winning. And then chlorine and tellurilium, which is down here. So 3.0 minus 2.1, difference of 0.9. So it's going to be a little bit polar as well. The arrow should point towards the calcium. All right. Thanks, you guys.